Hello, you're welcome back. All right, so let's continue from where we stopped. Now we are going to be looking at the electric potential of a charge conductive sphere. All right, so here is a diagram. So when you have a sphere, you know that already we've actually discussed the electric potential at a point due to a point charge. A point charge is just a small particle, just a point, okay? Just this point charge. If you want to represent point charge in an electric field, you can just use a dot. Okay, that simply is a single charge, positive or negative. All right, but now we are looking at a sphere. All right, so how do we describe the charge of a sphere? And of course, describe how do we describe the electric potential, okay, of this sphere? Now look at it. This charge distribution of a sphere is on the surface of the sphere from this diagram. All right. So anytime you see a sphere that is charged, the charge, okay, of that sphere is actually distributed on the surface of the sphere. So invariably now, if you want to calculate anything about any of these parameters, electric potential, electric field, then we should know that we're not looking at just a point charge. We're looking at charge distribution. So our question is, how do we apply the formula? Okay. Now it is much easier for us to um, for us to reduce this surface charges on the sphere to a point charge. How can we do that? If we trace the line of action of the surface charge, if I trace it, okay, in a straight line, all of them will meet. If you trace in a straight line, all of them will meet at the center. So, in conclusion, all right, we can say that the charge of the sphere, though they are on the surface, can actually be is traceable to be at the center of the sphere. All right, now let's look at a sphere having a radius of r. That way we can actually calculate the electric potential of the surface of the sphere. All right, since we are seeing the charge traceable, of course, to be concentrated, all the charges to be concentrated at the center to be a point charge. So invariably now the electric potential, by the formula that we already know, okay, is of course given as k q, which of course is the magnitude of the charge, then divided by the distance, which is r. Okay, so this is how we can actually calculate the electric potential on the surface. Now the question is, which part of the surface? The surface is at different points. The surface is not just a point, unlike what we've actually described before, right? That electric potential is measured at a point, but in the case of surface, we have different points. Okay, this is a point, this is a point, this is a point. So which point exactly? Now all the points on this surface is having the same electric potential, and which can be calculated by this formula. So when all the points in a surface is having the same electric potential, we call such surface an equipotential surface. Let me write it down. Okay, so a surface like this is what we refer to as equipotential. Equipotential surface. An equipotential surface is a surface of an equal potential. So any point, any point on that surface, all right, any point on that surface is having the same equal potential. So that simply means that since all the point in the surface is having equal potential, that we can say that the potential difference between 2 points in the surface is equal to 0. So, and if the potential difference is equal to 0, there is no work done in moving a charge in the surface. So the work done on the surface, since there is no potential difference, the potential are the same. So work done on the surface is equal to 0. Okay, so please take note of this. So this I just illustrated this term equipotential surface. Okay, so equipotential surface is a surface of an equal potential. Now, what happens to the electric field enclosed of by a surface? Okay, The electric field, please take note of this. The electric field inside the surface of a sphere is always equal to 0. Okay? So this electric field enclosed by a sphere is equal to 0. Then the electric flux also enclosed by a sphere inside the sphere, okay, is equal to 0. So please take note of this. So in case you have been asked, what is the electric field inside a closed surface? All right, not just a sphere, a closed surface is always equal to 0. So the only place you have electric field intensity that is not equal to 0 is outside the closed surface, but inside the closed surface is equal to 0. But we can actually calculate the electric potential inside the closed surface. So electric potential inside the closed surface is constant. All right, so it's constant at any point in that closed surface. Okay, so all right, so this is just a very simple illustration, and we're going to look at some more example. Let's look at a question that we have to solve. Okay, here we go. Okay, so this question goes this way. 3 concentric spheres of radii 4, 6, and 8 cm have the charges of +8, -6, and +4 microcoulombs respectively. What are the potential and the field strength? Field strength at the point 2, 5, 7, and 10 cm respectively. Okay, so this sphere I have actually drawn. Okay, 3 concentric sphere. So we have already been given their different radius. So the radius is 4, 6. So this is 4. Okay. Then of course this is 6. And this is 8. Okay. So they have their different charges. The charges are +8, -6, and 4 microcoulomb respectively. So we have to calculate the electric potential at different position. What are the position? Okay, let me just take this out so that it will look neat. All right, so what are the different positions? So first of all, we are being asked to calculate the electric potential and of course electric field intensity at this different position 2, 5, 7, and 10 cm. So let's start with the electric potential at position 2. Okay, so I can see electric potential V, let me use P2 to represent that first. All right, how can we calculate that? So position 2 is actually, let me call it okay, let me call it position 1, which of course is electric potential at position 1, VP1. Anyhow you want to represent, you can even call it V1, okay, just because they are all different. So that is at the point where the distance is 2 cm from the center. Okay, from the point where the distance is 2 cm from the center, that's where we are calculating the electric potential. And you know very well that electric potential, okay, can be calculated of a sphere, even inside the sphere. All right, so let's start. So we're going to calculate electric potential due to this charged sphere, the inner sphere, all right, the second sphere, and of course the last sphere. We are going to put them all together. So remember the formula of electric potential of system of charges, which is given as K Q1 all over R1 plus Q2 all over R2 plus Q3 all over R3. Okay, so let's start adding up. Okay, V1, the very first electric potential, is going to be, okay, we know already, is 9 times 10 raised to the power of 9. Then bracket open, Q1. The charge Q1, of course, is right here. Charge is 8 microcoulombs. Okay, that is 8. Now the question, what is the distance of that charge to 2 cm? Remember, the distance of this charge already, this sphere, the first sphere, the The radius of the first sphere is 4 cm, and the distance we are looking at is at position 2 cm. So from the surface of the sphere to the distance of 2 cm, okay, is 2 cm. So the surface of the sphere is 4 cm. All right, the distance we are looking at is 2 cm from the center. So from this surface to this distance is 2 cm. So that's what we're going to be using. That's going to be 2. Converting it to, of course, meter, that's going to be 0.02. Okay, then plus the second charge for the second sphere, all right, of course, is minus 6 microcoulombs. So invariably that minus 6 will definitely change this to minus. So I have minus 6. I have minus 6, then divided by the distance. The radius of the second sphere is 6, so I have to subtract 2. So invariably that's going to be divided by 4 cm, which is 0.04. Then the last but not the least, the charge of this third sphere, which is 4 microcoulombs, 4. Then divided by the distance. The third sphere is 8 cm, okay? Then subtract from 2, that is going to be 6 cm. So when you convert to meter, that will be 0.06. Okay. So at this point, we just calculate and do what we have to do. Okay. Now, okay, I forgot this. I didn't add the microcoulombs. So since this is times 10 raised power minus 6 times 10 raised power minus 6 times 10 raised power minus 6, which is a common factor, I can take it out. Times 10 raised power minus 6 outside the brackets. So let's get a calculator. So what I can do is, okay, so let's do, of course, this should be 400. 8 divided by 0.02 is 400. Then minus 6 divided by 0.04, okay, 250. Then plus 4 divided by 0.06. Okay, so I have 3.6, okay, 67 approximately. 316.67, please pardon me. Okay, so I have, this is 9, of course, this is going to be 9 times 10 raised to the power 9 times 10 raised to the power minus 6, that's 10 raised to the power of 3, then times what we've gotten here, 316, okay, 0.67. Okay, so let's do that multiplication. So multiply by 9, 2850, so 2850, and times 10 raised to the power of 3. Okay, so you can just write it this way. This is kilo. I can just put 2850 kilo. Okay, you can express it this way, kilovolts. All right, that is it for V1. What of V2? Okay, so okay, yes, not just the electric potential, we have to calculate E1. So E1 is equal to 0. The electric potential at that particular position is equal to 0. Why? Remember what I told you about electric potential previously. Okay, so electric potential at this point is a potential that is enclosed by the first sphere, second sphere, and of course the last sphere. So invariably that electric potential is equal to 0. So we'll go straight now to that electric field intensity, please pardon me, is equal to 0. So we'll go straight to the second electric potential. All right, so let me call that, of course, V2. Okay, so the same thing, we have the electric potential will not be 0 for any of these spheres. Okay, So we go the same way. All right, so which position are we looking at this time around? That is 5 cm. Okay, of course 5 cm is after the second sphere. All right, after the radius of the second sphere, 5 cm. So let's go. So that's gonna be still 9 times 10 raised to the power of 9, bracket open. All right, so q1 is still 8. Then the question is, what is going to be our r1? Okay, since the position now is at 5. Okay, now 5 cm. Now don't forget that the charge of each sphere is concentrated at, okay, is traceable to the center. Okay, don't forget, it's traceable to the center. Okay, I hope actually I applied that principle when calculating this. Yes, I did. Okay, so let's now proceed. So now what we have in this case, okay, now is the position is 5 cm. Okay, so since it is 5 cm, let's now look at how it goes from the second sphere, which is 4 cm, to 5 cm, that is 1 cm. Okay, from the second sphere, which of course is 5 cm, this is 5 cm. Okay, the second sphere, the radius of the the radius of the first sphere, please pardon me, the radius of the first sphere is 4 cm. Okay, the radius of the second sphere is 6 cm, and the radius of the third sphere is 8 cm. Okay, so now we are taking it one after the other. The distance of the first sphere, all right, from the charge, the surface charge of the first sphere to this point, all right, to that point, 5 cm. What is it going to be? That is from 4 to 5, that is 1 cm, which of course is 0.01. Then minus the second charge, which is 6. Okay, second charge, which of course is 6, divided by the distance of the circumference of the second charge, please pardon me. Okay, the distance of the circumference of the second charge to that 2.5. So the second charge we know is at 6 cm. Okay, so from 6 to 5 is still 1 cm. That is 0.01. Then plus the third charge, which of course is 4 microcoulombs, divided by the distance of the circumference of the 4 microcoulombs, which is 8 cm, if I'm not mistaken. All right, then to that charge, that's going to be 8 minus 5, which is 3 cm. So that's going to be 0.03. So don't forget to multiply by 10 raised to the power minus 6. Okay, so let's do this. So the second potential, V2, is going to be equal to, okay, so we divided this, gives me 800, this minus 600. Okay, then of course 4 divided by 0.03, what do we have? Okay, that's 133.3. So just approximately 133. So we'll have 800 minus 600, then plus 133. Okay, so that is going to be 333. Then I have to multiply by 9 times 9. 2899 2997. Okay, then of course times 10 raised to the power of 3. So you can express it in kilovolt. 2997 kilovolt. So that is what that entails. So now let's talk about let's look at how to calculate E2. Now this time around, let's see what is going to happen for E2. Now as you can see, E2 is outside, the electric field is actually outside the sphere, the very first sphere. Okay, so invariably I can calculate the electric field for the very first sphere, but for the second sphere, that the position is enclosed by the second sphere, and that same position is enclosed by the third sphere. So the electric field at that position for the second and the third sphere is equal to 0. So the only sphere that will be having electric field is actually the first sphere. So E2 is going to be equal to, you know, the formula KQ1 all over R1 square, right? Okay, so let's look at what we have. So this is going to be 9 times 10 raised to the power of 9, then Q1, okay, still remain 8. That's 8 micro, 8 times 10 raised to the power of minus 6, then all divided by the, of course, the distance we know already is 0 0.01, 0 0.01 square. Let's work on this. So invariably, what I have is 9 times 8, okay, of course, divided by 0 0.01, that's 7,200, okay, 7,200, then of course times 10 raised to the power of 3, which is 7200 kilovolts. So you can actually do that for, that's the same procedure, okay, is what you apply for the third position and of course the fourth position. So I hope you really understand. So I believe that you can actually complete that complete this solution. All right, so we are going to look at more in the next video. So see you in the next video. Thank you very much.